General relativity, step by step. Last time I was talking about these outgoing Eddington-Finkelstein coordinates, which had this rather peculiar property that outgoing null geodesics, outgoing light rays, seem to be able to get out with no problem, whereas inward light was effectively held up at the event horizon here. And the light cones tilted outwards rather than inwards. So it looked like gravity was repelling here. And we got this apparently new physics by nothing more than a mathematical trick. Well, did we? Well, it's not entirely it's not entirely straightforward what's going on here. So what we need to do is to transform to these things called Kruskal coordinates, or Kruskal Szekeres coordinates, and that sheds light on the physics that's going on underneath this. So I'll do that now. Okay, where was I up to? Here we go. So we had last time we had P was equal to T plus R plus, just pinch in a little bit, P equals T plus R plus log mod R over 2gm minus 1, and Q was equal to T minus R plus log mod R over 2gm minus 1. That's supposed to be an R. And before I go any further, I'm going to set 2gm equal to 1. So now we've got the Eddington coordinate P equals T plus R, R plus log mod R minus 1, and Q equals T minus R plus log R minus 1. I guess I could put brackets there as well if I wanted. Okay, so what I'm going to do now is to try and consider what life looks like, or consider what null geodesics at least look like in P and Q coordinates. So how do I do that? Well, of course, P, or a half P plus Q equals T, so that tells me that dt equals a half of, yes, we added them, dP plus dQ. And of course, if I subtract them, I get a half of P minus Q equals R plus log modulus R minus 1. Now, that modulus causes a lot of difficulty. Well, it's not difficulty, it is what it is. So we've just got to deal with it. So let's just have a think about differentiating this. This one's easy. We know that a half dP plus dQ equals dt. No worries. Now what about this one? Well, that's a little bit harder. That's a half dP plus dQ equals, and then I guess we've got two branches. They turn out to be the same, but we can consider R greater than 1 and R less than 1, and I'll show you that they end up as the same. So if R is greater than 1, we've got the differential dr times 1 plus the differential of log R minus 1, which is of course 1 over R minus 1, equals dr all over R minus 1, which is R minus 1 plus 1, which equals dr times R over R minus 1. I guess it's easier to write it like this, 1 minus 1 over R. That's a better way. Well, let's try developing this system for R is less than 1, and now we've got dr of 1 plus, actually no, it's 1 minus 1 over 1 minus R, which is of course the same thing, because I've just switched the signs and switched the sign of the denominator. So it's the same thing, it's dr over 1 minus 1 over R. So that's quite nice. How can we use that? Let's just write it out. dP plus dQ equals dr times 1 over 1 minus 1 over R, whether R is greater than 1 or R is less than 1. I guess the only place it fails if R equals 1 exactly, which you'd expect because something rather peculiar happens there in this coordinate system. Okay, so what I'm going to do now is to re-express the Schwarzschild metric. ds squared equals minus dt squared 1 minus 1 over R plus dr squared over the same thing plus the angular terms, which I'm going to ignore. And of course, as ever, I'm using units in which 2gm over c squared equals 1. And I think we've got everything at our. I think we've got everything here. So what I'm going to substitute for dt squared. Where's dt? Where's dt? Where's dt? It's here, isn't it? So it's equal to minus 1 over r times dt squared. From here, it's going to be a quarter dp plus dq. From this formula here, it's times 1/4 dp squared. Is it plus or minus? It's a plus 2 dp dq plus dq squared. Yeah, that's right. Plus 1 over 1 minus 1 over r, which is this term here, times dr squared. And from this formula here, we've got dr over 1 minus 1 over r. No, we haven't. I've got dr squared, so it's times a half. No, it's times a quarter dp squared minus 2 dp dq plus dq squared times 1 minus 1 over r squared. Why is it squared? It's squared because I'm considering dr squared, and when I take this denominator here up to the top on the other side, it's a numerator, not a denominator. Whew. Well, that's nice. So I can start cancelling. I think I can use my red pen for cancelling. So that term cancels with that square there. I'll use blue for cancelling individual terms. Everything's times 1 minus 1 over r. The dp squareds cancel because they're opposite signs. Look, that's a minus and that's a plus, because I'm using a minus plus 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 signature. This term cancels as well, and so we're left with these dp dq terms here. So I'll go back to black, if I can find it. There it is. And what have I got left? Now, I've got 1 minus 1 over r, which I'm going to take out. I'm going to take out a factor of a quarter, and here I've got a minus 2 dp dq, which is this term here, minus a quarter, 1 minus 1 over r, 2 dp dq. That's great. So we've got 4 of them all together. So it's equal to minus 1 minus 1 over r dp dq. That's right, because we've got 2 plus 2 equals 4, and we've got 4 on the bottom. So that's my line element squared, which I'm sure you'll agree is a nice, clean, clear, crisp, simple, easy to understand system. It's not diagonal. It would be nice. When you're considering your metric tensor, you want stuff on the diagonal and zeros out there. And here you haven't got that at all. Here, if you've got the P and the Q row and column, you have got zeros on the diagonal. And I guess it's a half. Have I got a factor of 2 mixed out? No, I don't think I have. It's easy to miss factors of 2 because of the 2GM thing. So that's minus a half, 1 minus 1 over r, minus a half, 1 minus 1 over r there. And zeros on the diagonal, which make life a little bit difficult. But nevertheless, we've got this beautiful, beautiful line element here, which incidentally shows that P and Q are both null coordinates. Because I know that my light travels along lines where ds squared equals 0, so that tells me that either dp equals 0 or dq equals 0. So these give me my null geodesics, which is quite nice. I'm going to stop there. Stop.